Welcome back, Lecture 12. This is Math 141, Calculus 1. I have a classroom of brilliant students in front of me right now, bright on a Monday morning. Some of those things are true. Most of those are true. It is Monday morning. That was true. Our goal this week is to wrap up the material on the syllabus prior to Test 1. I think we can get there. I'm not going to necessarily force the issue. If we don't have that done prior to Test 1, we'll still have Test 1 on Friday. It just will not cover the material that the syllabus says it's going to cover. But I think we can get there. If you're watching this on cable TV, test dates are different on cable TV. And if you're watching it on a later semester, obviously, even the units of kind of what's covered on Test 1 and Test 2, that potentially is different too. So if you're watching it later semesters, pay attention to the pacing guide, and that'll tell you what material is covered on Test 1 and when that's going to be. We're in the midst of wrapping up continuity. Let's review real quickly. This is from section 2.4. If you're going to see if a function is continuous at a certain point. So let's say at x equals a. Somebody tell me the first thing you would want to check. Pardon?
Does it exist at a?
Okay, does the function exist at a? So the f of a exists. So the question you're asking yourself, is there a point plotted there? If there's not a point plotted there, it's not continuous at that point. If it gets by that one, what's the second part of this continuity test or check that we do?
Does the limit exist?
Okay, the limit of the function, as x gets closer to a from both sides, it exists. Or does it have a limit as we're getting closer to a from both directions? And then part 3, if you get part 1 and part 2 and you miss part 3, you need to be slapped because you already have the 2 pieces to part 3, right? What is the kind of the final decision here whether this thing is continuous or not?
Is 1 and 2 the same?
Okay, the answer to 1 is the same as the answer to 2. So is this value that we're approaching, is it the same as the actual point that was plotted? If that's true, all those things are true, then it has to be continuous at that point. So if there is a continuity question on Test 1, which is a high likelihood, it's probably going to ask you to go through this 3-piece checklist. And at any point in time where it fails, you don't have to go beyond there. If there's not a point plotted there, make note of that. It's discontinuous. If it passes Test 1 and fails at Test 2, you don't have to go on to Test 3. So wherever it fails, you can stop the checking at that point. If we had something like this, kind of a lengthy function here, and basically we want to know what's happening as x gets closer and closer to 1, which is a bad value for this function because it kind of forces us to divide by 0, and even worse, it gives us 0 over 0, right? So we would have to do something with that. And in fact, it's okay in this circumstance to kind of slide the limit inside and save the, pardon?
What does that say?
Arc sign.
Oh.
You love my script, I know that. Thank you for the reminder. Arc sign or inverse sign. Go ahead and take the limit of the stuff that's going to kind of raise the issue anyway. And then when you're done, taking the limit of that stuff, then evaluate the arc sign of that. So let's spend a few seconds on arc sine. So if I have arc sine or inverse sine, so either notation, be prepared for either notation. What's that mean? What do we, let's say we had the arc sine of, I don't know, 1/2. There we go. That's exactly right. You're looking for the angle, or angles in this case, that have 1/2 for their sine, right? The sine of something is 1/2. Is that true? We're not taking the sine of something. That'd be just the sine function. This is an inverse sine, so we're looking for the angle that we could take the sine of that angle and get a specified number, in this case 1/2. If this is a lowercase a, meaning we want all the angles that have 1/2 for their sine, let's characterize this answer before we leave this example. Somebody tell me an angle that has 1/2 for its sine. I think I heard it. Maybe I didn't. Pi over 6, thank you. Now, is that the only angle that has 1/2 for its sine? No, there's a whole bunch of angles. So here's pi over 6. Is there another angle, kind of with the same reference angle, in a different quadrant that has 1/2 for its sine? 5 pi over 6. Good. So same reference angle, which that angle right there would be pi over 6. So that would be 5 pi over 6. That gets us over there. And is that, so are those two the only answers? They're, in one trip around, they're the only answers. In fact, in one trip around in a positive direction, they're the only answers. But we would say that the solution, really solutions, would be pi over 6 plus, and then any other angle that would end up there, right, at that same position in the plane, 2 pi n, where n is an integer, capital Z, by the way. And then what? 5 pi over 6 plus multiples of 2 pi added to that. So that should take care of all of the answers. And n, by the way, can be a positive integer or a negative integer. And you'll still end up at one of these locations in the plane. So it's not just finding an answer. This is where a calculator is helpful, but a calculator is not going to give you all the values. In fact, a calculator is probably going to give you that value only. And that's a start to the solution, but by no means is that the solution to this problem. Questions or issues with that? Yes. Alyssa.
Where did you get the n from? The n?
The n, this part. So we know that pi over 6 is, we know that the sine of pi over 6 is 1/2. We want all the other angles that terminate right here in the plane to also be a part of this solution. So if I came up here pi over 6 and went around another 2 pi, I would be back at this place, right? Or if I came up pi over 6 and went 2 pi the other direction, I'd be right here. So the 2 pi being the period in the sine function says that as long as I get 2 pi units away from pi over 6, I've got another solution. The n says we want integral multiples. So we want 1 2 pi added, or 2 2 pi's, or 3 2 pi's, 4 2 pi's, or negative 7 2 pi's. That brings us right back to here each time. And then the other one, same thing. We want to end back up here in the plane. We can start here and then again add multiples of 2 pi. So it adds integer multiples of 2 pi. Anything else before we put that aside, Blair?
What's the symbol between n and z? Far right.
Is an element of.
Okay.
N is an element of capital Z is a symbol that's pretty standard for integers. I don't know if you've used that before, but it's pretty standard. I'm not 100% why. I've heard that Z in German is something has to do with a counting number. Is anybody a German student in here? Like a counting number, an integer? Okay. Anyway, I heard that that's the origin of the capital Z for integers. I is already used. That's irrationals. Yes?
What did you use?
Brendan.
What did you use at half?
This is an example.
Okay, good.
Right. So I just chose a half because I knew the angle or angles would be fairly easy to come up with pi over 6 and 5 pi over 6. All right, last thing from 2.4 is called the intermediate value theorem. So you would expect with this being called a theorem that there's going to be some conditions, and if those conditions are met, then we can come up with some conclusion. The first thing that has to be true the function has to be continuous on the entire interval that we're examining. So if we're starting at A and ending at B, it's got to be continuous. If that is not true, then the conclusion that we're going to make in the intermediate value theorem, you cannot make that conclusion. And I'll try to show you a picture of why you cannot. So check that out first. Is it continuous on the closed interval? So we've got some value, capital N, that is sandwiched between the f of A and the f of B. I don't know if the f of A is smaller or the f of B is smaller. It's just in there in between. So we're going to find an f of A and an f of B. Capital N is going to be somewhere in between there. So here's a picture of where we are thus far. We've got a point over here at A, comma, f of A. And we've got another value over here, B. And again, it doesn't have to be true that f of B is above, but it does have to be true that we're dealing with some other point B, f of B, and it's got to be continuous. So I have to connect my two dots somehow. Straight line, curve, doesn't really say. I just have to be able to connect them. So let's say it just, I don't know, something. I'm connecting them. I've got to connect it because it's continuous. So if all these things are true, we have 2 points in the plane. We've got a continuous curve. Now, the intermediate value theorem, you would think it had something to do with the values in between, and it does. The values in between the f of A and the f of B, if we pick any of them, capital N is in there. If we pick any of them, so there exists a C value, and in fact possibly more than one, but the theorem guarantees at least one, somewhere between A and B, not at either end, but somewhere between A and B, somewhere between these 2 points, such that the f of this C value is capital N. So first thing to do, check out and make sure the function itself is continuous. If it's not continuous, we cannot draw this conclusion. We're dealing with a value N that's somewhere between the two endpoints. So here, let's say n is right here. I'm just going to pick an n value, somewhere between the f of a and the f of b. There's n. What this theorem guarantees is that if I come over to the curve and come down here, there is a guaranteed x value, in this case little c, lowercase c, such that the f of that c is going to give me that n value. So all of the values between f of a and f of b are used, so to speak. Some of them are used more than one. So let's say we pick our n value. I'll call it something else. I'll call it m right here. Is there a c value? I'll call it c1. Actually, there's another one, right? There's a c2. Actually, there's another one. But the theorem guarantees that there's going to be at least one. So it just so happens that the f of c1 is m, the f of c2 is m, and the f of c3 is also m. That's kind of above and beyond the theorem. The theorem guarantees one, at least one. So if it's discontinuous, if we don't kind of validate this first premise, do we have to be able to draw this conclusion? Well, let me draw one that's not continuous. So here's our A, f of A. And here's our B, f of B. Now, this is not continuous. So let me just draw a function that is, in fact, discontinuous right here. So it does this. Am I going to use all of the y values between f of A and f of B? No. In fact, we don't use any of them, right? So I come over here and I try to find an n value that's somewhere between f of A and f of B. Is there a value on the curve such that the f of some c is capital N? There is not. And there doesn't have to be because it's not continuous. So it is not guaranteed. Why? Function is not continuous. So that's the first thing to check. Is it continuous? If it's continuous, then we can go ahead and kind of find this value. So you say, well, let's just make it continuous. As soon as you make it, you connect this dot to this dot somehow, then is there a c value somewhere between A and B such that the f of c is capital N? Yeah, here it is. Come over here to the curve. There's our c value, right? As soon as you make it continuous, so really it kind of is a pretty reasonable, sensible theorem that if you're dealing with a continuous function, you are going to use all of these values as y goes from f of A to f of B as x goes from A to B. You have to. It's continuous. There's no gaps. There's no deletions. So hopefully it makes pretty good sense, the intermediate value theorem. So the theorem guarantees one value, but in some cases there might be more than one. So we'll have at least one value. All right, example problem. I can't remember if this is from your book or I got it somewhere else.
Did we ever finish that problem, the first problem you put up?
The what?
The first problem, the limit as x approaches 1 with arc sine.
That I didn't want us to finish it.
Oh.
I just wanted to look at the fact that it's okay if you have the limit on the outside. It's okay to move the limit into the inside.
Okay.
Maybe we should go back and finish that problem. Let's just see how this goes. Thank you for bringing that up. So we have a function. Here's our function. And there's our closed interval. So we want to use the intermediate value theorem. Show that there is a root. What's a root of a function? It's 0. The y value is 0. So we want to show that the y value takes on 0 somewhere as x goes from 1 to 2. So over this interval, well, first step, is it continuous? Is there any reason to believe that when you square something, it's going to cause any discontinuity of any type? This has a bad value, but are we close to that bad value? The bad value here would be -1, and then putting in values to the left of that would create a problem. But we're not even close to that. So over this interval, is this piece also continuous? So is there any reason to believe that this whole thing is discontinuous? It's continuous, isn't it? It's certainly continuous over its domain. So is it continuous? Yes, it is. But that's the first thing we have to check. If it's not continuous, you can stop the problem there because the intermediate value theorem is not going to help us. We can't use it. Okay? If we want the function to take on the value 0, we need to see where it is at 1 and where it is at 2, and hopefully 0 is somewhere in between those two values. So what's the f of 1?
0. -2.
1 minus square root of 2? Let's get a decimal approximation. What, -0.414? Does that sound right? 1 minus the square root of 2? F of 2? Four minus square root of 3? So 4 minus about 1.732. What is that? What is it? Thank you. Is this helpful? Are we going to be able to come to a conclusion here? The important thing is not that this is negative 0.414. The important thing is that it's negative, right? And not that this is positive 2.268, but rather that it's positive. Because what very conveniently is positioned between negative and positive numbers?
0.
0, and that's what we want. So, does the intermediate value theorem guarantee that because this function is continuous, because the f of 1 is negative and the f of 2 is positive, does it guarantee that there is a f of some c between 1 and 2 such that the f of that c is 0? Yes. So the f of c is 0 for some c. So as x goes from 1 to 2, the f of x goes from negative to positive. You can't go from negative to positive without somehow crossing through 0. So therefore, it's got a root. So by the intermediate value theorem, we are guaranteed a value. And in some cases, you are asked to find that value or find those values where that's true. But this was to show that there is a root, okay? We know there's a root. There is a solution to this. Here's a picture. I'm not really showing you anything you don't already know here, so this will be real brief. The f of 1 is negative. The f of 2 is positive. And we proved that the curve is continuous. So I have to connect the two green dots. I don't know what this curve looks like, but in order to get from the one dot to the other dot, what had to happen?
Had to cross 0.
Had to cross the axis. And the axis is where y is 0, right? Don't need to know exactly where it is. That's not part of this problem, but it does take on the value. F of c is 0 for at least one value between 1 and 2. All right. Had a brief discussion about limits involving infinity from the WebAssign. So that's 2.5. It might be appropriate as we're doing examples to bring up a WebAssign question. That's fine. We can use that as an example. But let's embark now in section 2.5. So limits involving infinity. So we may want the answer to the limit problem to be something infinitely large. I have a hard time saying that because it's not mathematically correct. If the limit is infinity, it truthfully doesn't have a limit, but it's good for illustration purposes. It tells you what the graph is doing. We can also then finish this section up by looking at what happens when x itself approaches infinity or approaches negative infinity. So we got couple different things going on in this section, but they do involve infinity. Either x is approaching that, or I guess technically y is approaching that. So let's talk about what the authors address as kind of valid according to this textbook, and then what is really mathematically kind of correct. Actually, let me make that an x squared down there so it doesn't matter which side we're coming in to 0. We could do 1 over x, but then we have to specify one side or the other. If the number in the denominator keeps getting smaller and smaller and smaller, so let's say x is 1/100th. What do we do with that? Well, we square it, and we throw it down to the denominator. So if you square it, it makes it even smaller, right? But it's smaller and in the denominator. So what is 1 over 10,000? That's 10,000, right? And if you let x get even smaller, then when you square it and it's in the denominator, it's even smaller. And when you take the reciprocal of that, it's even larger. So 1 over a million ought to be a million. So the question is, what is happening to these values? What's happening to 1 over x squared as x is allowed to get very, very close to 0? By the way, it wouldn't make a difference if this were positive or negative, right?
Right.
Because we're squaring,
Yeah.
so which is why I chose x squared down there instead of x. So as x approaches 0, what's happening to the value in the function? It's getting infinitely large, right? So is it permissible to say that the limit is infinity? That's allowable according to this textbook, okay? So if you want to say that the answer here is positive infinity, it's kind of like that's for illustration purposes only. That tells us what the graph is doing as we get closer and closer to 0. The best answer is does not exist. Now, WebAssign is tied to the book because these are questions from the book. So WebAssign is probably going to want this kind of answer, either positive infinity or negative infinity. But in reality, on a test or a quiz in here, it's certainly correct, and I think actually even more correct for you to say does not exist. If something is going to infinity, it's limitless, isn't it? It doesn't have a limit. It's headed to infinity, and that's not a limit. It's not a number. So for this book, positive infinity is okay. For a test in here, you could say positive infinity, or you could actually say does not exist. It doesn't have a limit. So the point that I think the authors are trying to make is that f of x increases without bound in this problem as x approaches 0. That is true. It increases without bound. It's boundless. It's limitless. Best answer does not exist. Acceptable for this book as far as homework problems, positive infinity or just infinity. Let's take some things we haven't looked at. The curve very often. And Blair, if that one question that you brought up before class, if you want to use that as an example when we finish that one, that's fine too. Natural log of x, and we want to come in from the right of 0. Why is that necessary? Because there isn't anything on the left of 0. So if you'll look at a natural log curve, doesn't it look something like this?
Yeah.
Is that a rough sketch of a natural log curve? So we can't come into 0 from the left. There is nothing over here. So we have to come into 0 from the right. And when we do that, we're letting x approach 0. What's happening to the y values? They're going toward negative infinity. Is that true? Or is she lying to us this morning? I think we can trust her. Just this morning. So again, for illustration purposes, it's okay to say the limit is negative infinity. Best answer does not exist. So I thought that would be a valid problem because I think it's worth looking at why you have to come in from the right, because the curve doesn't exist on the left side of 0. Blair, what was that one that you asked about before class? Do you have it? You don't have it?
I don't have to.
Okay.
It was limited as it approaches.
See if you can find it, and I'll find us another one.
Do you have to write positive infinity? Did you think that if you write like a number, you don't write like positive, like plus, or you just like.
You don't have to
just
write
like
positive infinity. That's right.
Okay.
Because we're talking about different versions of infinity, I usually put a plus and a minus in front of it, but the plus is not necessary.
It's the limit as x approaches infinity, x plus 2 over the square root of...
Okay, hold that. I didn't realize it was x approaches infinity, but jot that down because we'll get to that in just a couple minutes.
Sure.
These are where the y values are going crazy toward positive and negative infinity, and that's another type of problem where the x values are going crazy. Got to get trig in here. You know I'm going to throw lots of trig examples in when I can. Tangent of x, and we're going to get an inverse tangent in a minute too. I think it's an inverse tangent. Yes. We probably want to clean this up if we want this to have an answer. Tangent function. We know the tangent function does something like this because it's undefined at pi over 2. So I'm just going to leave it alone the first time through. If we allow x to get closer and closer to pi over 2, so we're going from both sides. As we come in from this side, what's happening to the y values? Toward positive infinity. As we close in on pi over 2 from this side, so as we're closing in from both sides, does this have an answer? This would be clearly a does not exist, right? Because from one side it's positive infinity and from the other side it's negative infinity. In fact, let's write those down. From the left side, from numbers smaller than pi over 2, we were approaching positive infinity, or as Catherine said, infinity. Now, in WebAssign, you have to spell out infinity, right? Mm-hmm. I think that's the way. There isn't a symbol for that. And as we come in from the right, the answers are getting closer and closer to negative infinity. I mean, you can't get a whole lot further apart than these two answers. So the answer to the two-sided limit would clearly be does not exist. But the one-sided limit answers, in fact, do have answers. If you want to call them that, you could also say they don't exist as well, and that'll suffice. All right, now we're headed toward, instead of the y values going crazy and going up toward positive infinity or down toward negative infinity, let's talk about what happens when the x values are allowed to get infinitely large or infinitely small. So let's say that x is going to approach infinity. And let's say that the function, in fact, has an answer, that it's approaching some specific number. We'll call it capital L. There's a lot of different things that could be going on graphically here. But here are some of them. So here's this value, capital L. So as x is allowed to get huge, maybe the function does something like this. And we see that nice, clean, simple, horizontal asymptote approach. We've seen that in graphs before. So as x gets huge, what happens to the y values? They get closer and closer and closer to L. So that might be the picture. It might, I'm going to just do this on the first picture, and then it might, in fact, be up here and close in on the other side. Same answer, right? As x is allowed to get huge, the y value gets closer and closer and closer to some number, capital L, from this diagram. Just because something is a horizontal asymptote doesn't mean that the graph can't cross it. In fact, sometimes it does cross it. The graph's not undefined at that value. It just eventually approaches that value. You could actually have a curve that came in here, crossed the asymptote, and approached it from the other side. Is it a true statement that as x approaches infinity, the y value is getting closer and closer to L? That's true. So we do sometimes need to check to see if it crosses it. It's only a valid statement for x approaching infinity. This is not very close to infinity right here, so it's possible it may have taken on L there as well. On a rare occasion, you'll find a function that will cross an asymptote several times. And then eventually, as you work your way out to the right, it approaches that. This would be something that would have a descending amplitude, right, as you go. And eventually, way out there to the right, it doesn't go too far above capital L, nor does it go too far below capital L. So eventually it does, in a sense, approach capital L. Catherine?
Is that something called like oscillating? Or
Yeah.
Like where it's going
Yeah,
like
that would be an oscillating function, but it would have a diminishing amplitude. So that amplitude is getting smaller and smaller as you go. How might you accomplish that in an equation? If you wanted to have a decreasing amplitude. Doesn't, in a function, doesn't the number that occupies this position, doesn't that affect the amplitude? So suppose you wanted that to kind of degrade as you go.
A divided by x.
Okay. Somehow or another, fix this up so that it causes the amplitude to get smaller as you go. A nice convenient way would be to put in like e to the negative x there, right? Isn't that a decaying function? So it causes the amplitude to decay. There are lots of ways you could put something in there that would cause this net effect on an oscillatory function. All right, now I'm ready, Blair, for your example. This is a web-assigned question, so let's just make it an example.
The limit is x approaches infinity, x plus 2 over the square root of 16x squared plus 1.
That's all under the radical?
Yeah.
16x squared
Plus 1.
plus 1. Okay. We haven't done anything quite like this yet, so it's probably pretty good that we did this one in class. If x is approaching infinity, does this plus 1 really mean a whole heck of a lot?
No.
If you had $16 trillion and you dropped one, would you kind of bend over to pick it up?
Okay.
Probably not. Okay. I want to follow that person because they're probably not going to bend over to pick up a 20 or a C note or something else either. But that plus 1 is pretty insignificant. So wouldn't you say the dominant term under the radical is the 16x squared, right? Clearly going to dominate that little plus 1. Well, eventually, when x approaches infinity, isn't the square root of 16x squared plus 1, isn't that eventually, as x approaches large values, that's going to be pretty darn close to just 16x squared.
Yep.
Does that, everybody believe that?
Yeah.
Mm-hmm.
The plus 1 gets more and more insignificant the further out to the right that you go. And if it is the square root of 16x squared, that's pretty close to just 4x, right? So the denominator is not reducible. It's the square root of a sum. So only in the limit problem can we examine what happens to this. It gets close to that, which is exactly 4x. So this problem is very close to this problem. Not very different from that problem at all. It is a different problem. So, but for large values of x, the answers to these two are the same. Now, we haven't talked about shortcuts yet, but let's develop one of our shortcuts. So is everybody convinced that we can really look at this problem instead of this problem for large values of x? So if you examine, and we'll have really 3 cases here, and I think we can probably hit all 3, and then we'll have to stop today. If the degree of the numerator, well, let me go back a step. These 3 cases are only cases that we need to consider when x is approaching infinity. If x is not approaching infinity, we've already gone over how to do problems lots of other ways. But in this case, if you look at the numerator and the denominator, and they are of like degree, which they are, x to the first over x to the first. Divide by that degree of x. So in this case, it's x to the 1. So x over x plus 2 over x. We'll have a shortcut, too, so you don't have to do this every time. But this is your backup to the shortcut. This will work every time. X over x is 1. 2 over x we're kind of stuck with. 4x over x is 4. What happens to 2? Quick question, Blair.
Oh, I was just about to say what you were saying.
Okay. So what was my question going to be?
You were about to say what is 2 going to be when x approaches infinity, which is going to end up being just next to 0 because it's divided by a very large number.
Okay. Everybody follow that all right? He asked the question and answered it. I'm virtually unnecessary up here. So 2 over x, as x approaches infinity, that gets smaller and smaller and eventually approaches 0. And so the answer to this is 1/4. Now, do you see a shortcut, or have you used a shortcut in the past? Katie, right?
Ratio of the coefficients if the degree is the same.
Okay. If the degree is the same and x is approaching infinity, only this particular category of limits, degree of the numerator and denominator are the same, it's the quotient of the lead coefficients, because we have 1x over 4x, 1/4. Is that okay? How many of you have used that before? Okay, most of you. If you haven't, you can always fall back on this as the backup to the shortcut. So since this problem is so very, very close to the problem that Blair mentioned that was on WebAssign, the answer to this is 1/4. That little plus 1 is not going to change the answer. Way out there to the right. What if the degree of the numerator is less than the denominator? I'm just making up a problem. So way out there to the right somewhere as x approaches infinity. Anybody remember that shortcut? Okay, well, let's just use our backup. Look at the degree. Well, let me go back a step. X is approaching infinity, so it's going to fit into this little subset of what we're examining. X to the first in the numerator, x to the second in the denominator. So the largest degree that we see is x to the second. So 3x over x squared simplifies to what? 3 over x. Can't do much with 1 over x squared. 2x squared over itself is 2. 5x over x squared. 5 over x, and 8 over x squared we're stuck with. All right. What happens to all the terms that now have a number over some value that's getting increasingly larger? Don't they all disappear?
Yep.
Okay. This one, as x approaches infinity, that goes to 0. This one goes to 0. This one goes to 0. And this one goes to 0. So they just disappear. They're practically insignificant way out there to the right somewhere. So we end up with 0 over 2, which in this case is 0. Will the answer always be 0 when x is approaching infinity and the degree of the numerator is less?
Yeah.
Yes. Morgan, right? Trying to learn names. I'm getting there. So in this category, when x is approaching infinity and the degree of the numerator is less than the degree of the denominator, you could do this. That's fine. This will always serve as a backup, but you can go directly to this. The limit is 0. Now, what's another way of justifying that doesn't use this algebra stuff? When the degree of the denominator is larger, isn't the denominator getting larger at a faster rate than the numerator?
Yeah.
Is that true?
Yeah.
You're putting in larger and larger values for x, So the numerator is getting large, 2 over 5, and then it becomes 8 over 100, and then it becomes 15 over 10,000. But when the denominator wins like this, what happens to the value of that fraction? It gets smaller and smaller and smaller and eventually approaches 0. All right, now I'm not going to write this down, but the third case is exactly the reverse of this, and we're just about out of time, so let's wrap it up here in about 30 seconds. Just flip everything we have on this sheet of paper. We end up with 2 over 0. Does not exist. When the degree of the numerator is larger than the degree of the denominator, it doesn't have a limit. It's limitless. It does not exist. Why? Because the numerator is winning, and when the numerator wins, you're not closing in on any one specific value. It doesn't have a limit. So those are the 3 cases there. All right. Thanks for your attention, and we will reconvene tomorrow.